Okay, and then where we left off in the first part was an example where we are going to try to find the pH of each solution given the H plus concentration, or H3O plus concentration, or OH minus concentration, as the case may be. So in this case, all the book told us was that we had an 8.0 times 10 to the minus 4 molar solution of KOH. Now, remember, KOH is a strong base, and there's only one hydroxide ion in it, in each formula unit of the compound. And so it's safe to assume that the OH minus concentration is going to be 8 times 10 to the minus 4, just like the concentration of the compound itself. Well, for the pH, we need the H plus ion concentration. And for that, we're just going to take Kw divided by the OH minus. And so that's 10 to the minus 14 divided by 8 times 10 to the minus 4, which gives us 1.25 times 10 to the minus 11 for the H plus concentration. But we're not done yet because we want pH. pH is the negative log of the H plus ion concentration. So you want to take the negative log of 1.25 times 10 to the minus 11, and that should give you a result of 10.9. To actually do that, you can, okay, I guess you can see that. Just go negative log, and then what was it, 8.0 times 10 to the minus 4? And you get, say, wait a minute, what? Oh yeah, sorry, 8.0, I was using the OH minus concentration. Well, actually, to get a little bit of ahead of things, there is a similar concept known as POH, where you can take the negative log of the OH minus concentration, and the POH for this solution, because I mistakenly took the negative log of the OH minus concentration, the POH of this solution is, therefore, 3.10. Okay, and it turns out that pH is equal to 14 minus POH. So if you take 14 minus 3.10, in this case, you end up with, guess what? 10.9. But let's do it the right way. And we'll say a negative log of the actual H plus concentration. So it's going to be negative log of 1.25 times 10 to the minus 11, close parentheses. And we have, well, 1.09 times 10 to the 1, because I put it in scientific mode a while ago. So that's 10.9. And that's exactly what we expected. Okay, so the other one they wanted us to look at was 0.0015 molar HCl, and that gives us an H plus of 0.0015, because again, HCl is a strong acid, and there's one H plus ion per molecule. That is one acidic hydrogen per molecule. And so you can assume that the H plus concentration is the same as the concentration of the acid. And so if you want pH, you just take the negative log of that concentration, and you get 2.82, which is less than 7, so it's acidic. Just like 10.9 was greater than 7, and so that's basic. And there is one more part where we had 6.65 times 10 to the minus 5 molar NaOH. Sodium hydroxide is a strong base, so it will dissociate completely into ions. And there is one hydroxide ion per molecule. And so you can assume that the hydroxide ion concentration ends up being what the original concentration of the acid was, which is 6.6 times 10 to the minus 5 molar. The H plus concentration is Kw divided by that, or 10 to the minus 14 divided by 6.6 times 10 to the minus 5, which means the H plus concentration is 1.5 times 10 to the minus 10. And because the H plus concentration is less than 10 to the minus 7, that tells you the solution is basic. So you could answer that question now, or you could wait for the pH. pH is the negative log of the H plus concentration, and that is 9.82, which is greater than 7. So yes, it's definitely a basic solution. The need might arise, though, to go the other way. Maybe pH in the lab, especially, is very easy to measure. And so there may be cases where you have the pH of a solution and you want to know what is the H plus ion concentration. And so that's a pretty common calculation. And what you do is you just reverse the calculation for pH. If pH is the negative log of the H plus concentration, then the H plus concentration would just be 10, the base of the log system, raised to the power of negative pH. And so H plus is 10 to the negative pH power. So whatever number the pH is, make it negative, raise 10 to that power, and that's your H plus ion concentration. Now, of course, you can't necessarily just leave it that way unless the pH is a whole number, because our answer for the concentration has to be either in proper decimal or scientific notation form. And like 10 to the minus 2.3 is not proper scientific notation. So all you have to do in that case is just enter that number into your calculator and hit equals, and your calculator will tell you what it is in proper decimal or scientific notation. So here we have, we want to find the H plus ion concentration for each of these solutions. A solution where the pH is 12.3, which tells you right away that it's a basic solution. That means the H plus ion concentration would be 10 raised to the negative 12.3 power. And if you do that in your calculator, you just take 10 and raise it to the negative 12.3 power and hit equals, and it gives you 5.01 times 10 to the minus 13, which is just what it is. Okay, pH of 7.05. Now, if this were pH, if this were a case where the pH is equal to 7.00, then all you'd have to do is say H plus is 10 to the minus 7. But it's not quite 0.00, it's 7.05. And so H plus is going to be 10 to the minus 7.05 power, and that comes out to be 8.91 times 10 to the minus 8 molar. And with a pH of 7.05, I guess it's technically basic, but just barely, because 7, of course, is neutral. And this is just a little bit above that. For a pH of 1.4, that's well below 7. So this is an acidic solution. The H plus concentration is going to be 10 to the minus 1.4, which comes out to 3.98 times 10 to the minus 2, which is acidic. There's a table on page 719 that's kind of interesting. It gives you pH values of typical pH values, that is, of commonly encountered acids or bases, things like soft drinks or stomach acid, things like that, which is kind of interesting to see. Your stomach acid is actually very acidic. It often has a pH as low as 1, and it is hydrochloric acid, so it's a strong acid too. Here's an example where we calculate the H3O plus ion concentration, or H plus ion concentration, if you prefer to call it that, in peanut butter that has a pH of 6.3. Well, the pH is just going to be, the H plus ion concentration, and the H didn't come out very clearly either. The H plus, that's H plus in brackets, is going to be equal to 10 to the negative pH power, and that's 10 to the negative 6.3, or 5.01 times 10 to the minus 7. Now here is where we come to the concept I mentioned a moment ago of POH. Sometimes when you have, especially when you have a base, it's easier to calculate POH than it is pH. Or it's easier to calculate POH first and then calculate pH from that. And so there's the analogous concept of POH, which is just the negative log of the OH minus concentration. It's derived from the fact that Kw is equal to H3O plus times OH minus equals 10 to the minus 14. And so, using the rules of logarithms, it's also true that for any aqueous solution, the pH of that solution plus the pOH of that solution always add up to 14. And the way that we would actually use that equation, again, is to find one or the other of these when we know one of them. Because we know pH plus pOH add up to 14, we're not going to use the equation in this form very often. So quite often we'll use it in the form pH equals 14 minus pOH. And sometimes we'll do it as pH equals 14 minus pH. So both of those are always true of any aqueous solution. Whether it's acidic or basic or neutral, or even if you don't know. All three of these equations are true if it's an aqueous solution. So it's important, though, to keep in mind that the trend for pOH is the opposite of pH. So for pH, 0 means very acidic. For pOH, I mean, 14 means very acidic. And for pH, 14 means very basic. For pOH, it's 0 that means very basic. But actually, they agree on one thing. 7 is neutral either way. Okay, so we've got an example here where we're trying to find the pH of a solution that has an OH minus concentration of 7.7 times 10 to the minus 10. Now, in questions like this, where you're kind of crossing over, so to speak, from like you're given information about OH minus, but you're asked to find out something about H plus or vice versa, there are usually, well, two ways that you can do it. Sometimes one is easier than the other. Sometimes they're both about equally difficult, but there are indeed two ways to do this question here. You could take the OH minus concentration and use that to find the H plus concentration and then find the pH. In this case, what you do is you'd find the H plus concentration as Kw divided by OH minus, which is 10 to the minus 14 divided by 7.7 times 10 to the minus 10. And that gives you 1.29 times 10 to the minus 5 for the H plus concentration. And then you just take the negative log of that and you have your pH, 4.89. The other way you could do it is to, and this way is actually a little bit easier in a problem like this, is take the OH minus concentration and first find the pOH and then find the pH. Because the pOH is just going to be negative log of the OH minus concentration, which was the 7.7 times 10 to the minus 10. Take the negative log of that, you get 9.11. And then take 14 minus that, and you've got the pH, which, what do you know, 4.89. So either way will work. And here are a couple more examples. There are also two ways to do each of these, but I'm only going to do them one way just to save some time. Okay, so 610, you want to calculate the OH minus and pH of the following. So in this case, it doesn't really matter what you're given. You're going to have to find something related to OH minus and something related to H plus. And so you're going to have to use one method or the other of the two that I just showed you in the last example. If you're given 0.005 molar HCl, and again, HCl is a strong acid, and there's only one acidic hydrogen per molecule, you can assume that the H plus concentration is 0.005. The pH will be the negative log of that, which is 2.30. Okay, so we found the pH. You don't necessarily have to find the information asked for in the order that it's asked for. So you're perfectly free to find the pH first and then the OH minus. Just make sure everything is labeled so it's clear what's what. So now that we know the pH, we can go back to the original information and find OH minus. The original information was that H plus is equal to 0.005. So the OH minus concentration is going to be Kw divided by that, 10 to the minus 14 divided by 0.005, and that will be 2 times 10 to the minus 12 molar. Okay. In the second part, we are given a concentration of sodium hydroxide. Now, actually, this turns everything around. Notice the concentration is the same as the concentration of the HCl. So everything here is going to be kind of the opposite of what it was up above. This is sodium hydroxide, strong base, 1 hydroxide ion per molecule. So you can assume that the OH minus concentration is the same as the concentration of the base. This time, since you've got OH minus, you can find pH as just 14 minus POH. POH would be the negative log of the OH minus concentration, which the OH minus concentration is 0.005. So you take negative log of 0.005, you get 2.30. So 14 minus the POH, which is 2.30, gives you 11.7 for the pH. I mistakenly put an O in there when I originally wrote the notes, but that's just pH is 11.7. Okay, so you found the OH minus and the pH. For measuring pH in the lab, we've done that in lab already, so you're fairly familiar with that. There are a couple of different ways you can do it, and some are easier than others, while others may be harder but more accurate. One would be acid-base indicators, and acid-base indicators are basically dye molecules, molecules that absorb visible light of certain colors, and therefore when we look at them, we see the complementary colors. Like if something absorbs green, we see red, that kind of thing. And the thing is that these are large, complicated molecules that have several places where acidic H pluses can bond onto the molecule. And at different pHs, different pH levels, that is different concentrations of H plus ions might attach or detach from those areas on the molecule. And what results from that is a difference in the way the molecule absorbs light. So if the molecule starts absorbing a different color of light, it will appear a different color to us. And so, scientists have gone through these molecules over the years and sort of cataloged at what pH level does each indicator change colors from one color to another. And so by using an acid-base indicator, you can usually narrow down what pH range your solution is in just by looking at what color the indicator turns when you put it in your solution. A good example is our old friend phenolphthalein. It's simple anyway, from pH from 0 up to 8.5. So anything that's acidic or neutral or slightly basic will be colorless, but anything that's significantly basic will be pink. And that's just because of the way the number of acidic hydrogens that are on the molecule in acidic solution versus basic solution. Other molecules have different structures, and so they will change colors at different pHs from phenolphthalein. And some molecules will actually have more than one location where acidic hydrogens can come or go from the molecule, and they can have more than one color change throughout the pH range. And for those, you can really narrow down what your pH is. There's also pH paper, litmus paper, which is what we always used to use in the lab, was soaked in an acid-base indicator called litmus, hence the name. And the litmus is kind of like phenolphthalein. It's not very versatile. You can tell whether your sample is acidic or basic, and that's about it. Now we tend to use universal pH paper, which is porous paper that's been soaked in several different acid-base indicators. And so universal pH paper can turn a whole variety of colors depending on what the pH is. And universal pH paper often makes it possible to narrow down the pH range of your solution to like 1 or maybe 2 pH units, which is pretty good for just sticking a piece of paper in it. There's also the pH meter. pH meter is an electronic device, of course, that involves a porous glass bulb. That's the electrode. Well, actually, the electrode technically is inside the porous glass bulb. And inside that porous glass bulb is an acidic solution, a solution of H+ ions. When that bulb is placed into a solution that contains a different concentration of H+ ions, then H+ ions will travel through the glass membrane one way or the other, either in or out. And the electrode measures that electrical current because H+ ions have a positive charge on them. So when they move from one place to another, that's an electrical current, sorry. And the electrode measures that, and the electronics inside the instrument can convert that to a pH reading. And so the pH meters are very versatile. They are now, actually, modern ones are pretty easy to use, but they do require a certain amount of care, and they do have to be calibrated before you can actually use them, unlike the pH paper, for instance. But pH meters usually give you pHs to the nearest hundredth of a pH unit, which is way better than you can ever get from pH paper or indicators. Okay, so that's measuring pH. That's mostly for the lab, though, so we won't spend too long on that. Weak acids and bases. That's something we had to talk about sooner or later. And we've actually just talked about equilibrium a little while ago. So a lot of the stuff that we deal with in weak acids and bases should be fairly fresh, because the dissociation of a weak acid or base is, in fact, in equilibrium. And that means that the percent ionization or the percent dissociation for a weak acid or base will be less, not only less than 100%, but normally way, way less than 100%, like 10% or less. 10% is on the high side, actually. And so we don't, if for a given weak acid, say if you have a 0.1 molar solution of acetic acid, and you want to know what the H+ ion concentration is, you cannot assume that the H+ ion concentration is the same as the concentration of the acid, because we don't know how much the acid dissociates. We don't know how many of those molecules of acid in solution are actually going to give off H+ ions into solution. We know it's not going to be all of them. In fact, we know it's not going to be anywhere near all of them, but we don't know how many. And so we have to go through a series of calculations involving ice tables and fun stuff like that in order to find out how many of those molecules will be ionizing and what the H+ ion concentration is at equilibrium. So we don't know what the H+ ion concentration is just from the concentration and identity of the acid, but we do know that the H+ ion concentration is going to be much less than the initial concentration of the acid. And the same with weak bases. We know the OH- concentration is going to be much less than the initial concentration of the base. But without calculations, we don't know how much less. An example of a weak acid is acetic acid. Our book likes to write the formula as HC2H3O2, which is kind of, makes it look like an inorganic acid. It can also be written as CH3COOH. And again, that ending COOH tells you right away that it is definitely an organic acid, and therefore it's also a weak acid. And notice how the formulas work out the same. You've got the acidic hydrogen at the beginning when you write it as HC2H3O2. The acidic hydrogen comes at the end when you write it ending in COOH. And we've got 2 carbons. Well, 1, 2, they got 2 carbons. 3 hydrogens beside the acidic hydrogens. Well, there they are, 1, 2, 3. 2 oxygens, 2 oxygens. And the reason the molecule is, or the formula is often written as CH3COOH is because this is what it looks like. So you can actually see quite clearly CH3COOH. And, again, I like to write it that way just because it makes it obvious without a doubt right away what it is. But anyway, the weak acid plus H2O will yield H3O plus, in this case, the acetate ion. And these are the two different ways that you can write the acetate ion. The acidic hydrogen, remember, is the one at the end of the formula, which is the one I just circled here. When you write it the way the organic chemists write it. Or it's the one that's up front if you write it as HC2H3O2. And so I just circled that, but that's the hydrogen that's leaving and going to the H2O. And what's left over is known as the acetate ion. The equilibrium constant for this reaction, since acid bases is sort of a specialized use of equilibrium constants, this equilibrium constant has been given a special name. The equilibrium constant for the dissociation of a weak acid is called Ka, for equilibrium constant of the dissociation of an acid. And that's just products over reactants. So it's H3O plus times acetate ion concentration over the remaining equilibrium concentration of acetic acid. Notice though, the H2O, remember, does not appear in the equilibrium constant expression because we don't include pure liquids. Okay. So in general forms, when we want to represent a weak acid without actually saying what it is, we usually write it as HA, where H stands for the acidic hydrogen and A just stands for anion. It could stand for the acetate ion like it did up here, or some other anion. And the dissociation will give you H plus A minus, or you could write it as HA plus H2O yields H3O plus A minus. Again, either way is fine. And the Ka will be products over reactants. So H plus times A minus over HA. And in general, for a base, we'd represent a weak base as just B, and B standing obviously for base. And when that interacts with H2O, we get BH plus, because remember, bases are proton acceptors. So the B ends up with an H plus attached to it. So it's BH plus OH minus, which is what's left over from the water when you remove an H plus. And the equilibrium constant for the dissociation of a weak base is called Kb, and that would be BH plus times OH minus over the remaining equilibrium concentration of B. And you can substitute in formulas for other weak bases, like for instance ammonia. Ammonia is a weak base, and when you put it in water, it will come to equilibrium with its ionization products, which are NH4 plus and OH minus. Notice that NH3, being a base, takes in NH plus from water and ends up with one additional hydrogen and a positive charge. So NH3 becomes NH4 plus. H2O, when you take an H plus ion away from it, becomes OH minus. Kb here will just be NH4 plus times OH minus over the remaining equilibrium concentration of NH3. And that will be equal to a number. In this case, that's 1.8 times 10 to the minus 5 at 25 degrees Celsius. Actually, that number just happens to be the same as the Ka for acetic acid at 25 degrees Celsius, 1.8 times 10 to the minus 5. So you'll be encountering that number quite often in this chapter. Because Ka and Kb's have complicated numbers that often involve negative exponents, scientists have also decided that they often want to use a log system similar to pH in order to simplify comparing Kas and Kb's to each other, so that you don't end up with all kinds of negative exponents and things like that. And so pKa, remember I mentioned that P is just a symbol that means negative log of something. So pKa is just the negative log of Ka. And Ka is just, and you can reverse that if you want the Ka and you have the pKa. Ka is just 10 to the negative pKa power. So the Ka of acetic acid is 1.8 times 10 to the minus 5. the pKa of acetic acid would be the negative log of 1.8 times 10 to the minus 5, which is 4.74. And something I didn't think to write in, but I will now, is if you have the pKa and you want the Ka, as I said, that's just 10 to the minus pKa. For acetic acid, that's going to be 10 to the minus 4.74. And guess what you get if you put that into your calculator? Whoops. 10 raised to the power of negative 4.74 equals 1.8 times 10 to the negative 1, 2, 3, 4, 5. So it works. It works similarly with pKb. pKb is the negative log of Kb, and Kb itself is 10 to the negative, 10 to the negative pKb. 10 to the negative pKb. The Kb of ammonia is 1.8 times 10 to the minus 5, and therefore the pKb for ammonia is 4.74. And again, you could do this, the Kb, or sorry, if you want the Kb back, and you're too lazy to look back to the beginning of the question, you could just take 10 to the minus pKb. Which gives you 1.8 times 10 to the minus 5. Basically, the acid strength tends to trend along with the value for Ka. So if, the bigger Ka is, the stronger the acid is. But when I say stronger here, I mean less weak, because only weak acids have Ka values at all. The Ka value for a strong acid is essentially infinity. So if you have a number for Ka, that right there tells you the acid is weak. It may be a relatively strong weak acid or a relatively weak acid, but it's weak overall. And smaller Kas mean weaker weak acids. Same with Kb. Larger Kbs mean stronger, or in other words, less weak bases, but they're still weak. And a smaller Kb means a weaker base. Okay. Now remember, pKas and pKbs have the opposite trend. Because pKa and pKb are negative logs of Ka or Kb respectively, that means that it switches the magnitudes around. So for a stronger acid, you want a smaller pKa. And a bigger pKa, in fact, means a weak acid. Kind of like a smaller pH means a more acidic solution, and a higher pH means a less acidic solution. Okay, we can quickly just look at this example of calculating Ka and Kb. For ethylamine, the book gave us the pKb being 3.20. So if you want the Kb, which wasn't there originally, you just take 10 to the minus pKb, that's 10 to the minus 3.20, hit equals, and you get 6.31 times 10 to the minus 4. For the second example, methylamine, it gave us the Kb and wanted pKb. So if you got the Kb and you want pKb, pKb is just the negative log of the Kb, and that's going to be 3.30 in this case. Okay, and gone a little over what I wanted to do, sorry, but that got us to the end of this portion anyway, and we'll pick up there hopefully in person on Monday. Okay, so we'll see you then. Oh, and I will get the chapter 16 homework problems up on Achieve today. Definitely, I promise, because I'm sure you're waiting for them. Okay.